So let's review what we learned last week about series DC circuits. But first, I want to look at our prefixes again and just make sure you understand. First of all, make sure you've memorized at least the first, 4 of these. So so you should know micro, milli, kilo, and mega for sure. When we get to capacitors and inductors, it'll be important for you to know pico and nano. And giga and tera we really probably won't even get to, but you shouldn't at least know these 4 right now. So when you're talking about mathematical operations, and I'm just going to talk about multiply and divide, for instance. So when you multiply and divide, remember when you multiply, you're adding the powers of 10. So if you multiply, let's see, milli times kilo, remember that's 10 to the negative 3, something times 10 to the third. And so when you do that, you get 10 to the negative 3 plus 3, which is 10 to the 0. So basically, if you are at milli, and milli plus kilo, that gives you no prefix at all for your answer. And if you take micro and you multiply by kilo, that's negative 6 plus 3, where the answer would be negative 3. So that would be milli. So if you have microamps times kilo ohms, you'll end up with millivolts for your answer. Let's see, what about if you multiply mega ohms by milliamps? That's negative 3 plus 6, so your answer would be kilo ohms there. Okay, so, and then dividing, when we divide, so let's say we take milli divided by micro. So that's 10 to the negative 3 times something times 10 to the negative 6, where that would be 10 to the negative 3 minus a minus 6. Okay, so negative 3 minus a minus 6 is 10 to the 3. So when you're dividing, remember you're going to have, like, let's say milli divided by micro, negative 3 minus a minus 6 means your answer is going to be kilo, or 10 to the third. Let's say you've got mega divided by kilo. 6 minus 3 is 3, so your answer would also be kilo. So keep working on your prefixes, and at least make sure you know micro, milli, kilo, and mega. So let's look at a series circuit. This is from last week. I just want to review. So if we're looking for our unknowns here, we're looking for the voltage source, the V2 here, V4 here, and the current. So what I'm going to do here, since we can't really find RT, since we don't know R3, and we can't find I sub S, even if we did, because we don't know E, what you want to do is look for a place in the circuit where you actually have, 2 of either voltage, current, and resistance. So if you have 2 of those, you can get the third. So where we have that is actually right here. You've got the voltage drop across R1, and the resistance of R1 is 1K. So that will give us the current, right? So I1, which is V1 over R1. Remember from our subscript notation, V1 is the voltage drop across R1. R1 is the resistor, of course, R1, and I1 is the current through that resistor, R1. So we're giving us 2 volts across 1K ohm of resistance. So that means we must have 2 milliamps of current through our resistor R1. So I'm going to draw that in, and remember our current is going to enter on the more positive side and leave on the more negative side when we're talking about a voltage drop, because it's going to take energy to push that current through there. So that's 2 milliamps of current through there. Now, this all of these resistors are in series with each other, and they're in series with our voltage source. So that means that we have the same current throughout the circuit. So that same 2 milliamps would be over here, it would be here, and that's what's coming from the source. Okay, so now that we have that, we can find a good bit of more information here. For instance, if we want the voltage drop across R2, we now know the current through there, and we know the resistance, so we can find V2. So V2 is going to be I2 times R2. Again, just Ohm's law here. So the current through R2 is our 2 milliamps. And the resistance is 2 kilo ohms. So we must have a 4 volt drop there. So that must be 4 volts. All right. Let's see. We can find V4 as well. I think since we're working on voltage, let's just stick with V4 for now. So V4 is going to be the current through R4 times R4. Now, the reason I'm writing it this way, V4 equals I4 times R4, is because in every circuit that you're ever going to work, whether they're series parallel combination, or whether the resistors are not in series or parallel, in any circuit, this is true. The voltage drop across a resistor is the current through the resistor times the resistor value. And it does not matter what the configuration is. This is always going to be true. So that's why I write it this way, so that you'll hopefully always remember that that's true. So we've got that same 2 milliamps in this case through R4, and R4 is 3 kilo ohms. That means that must be a 6 volt voltage drop there. So I'm going to write that in here. And what else do I have left? I have left to find R3. Okay, so R3 right here. I know the current through R3, and I know the voltage drop across R3. So I'm looking for R3, where that is V3 over I3. The other thing is, make sure you're getting Ohm's law right, okay? If you get it wrong, that's a pretty big problem, so make sure you're getting this right. Okay, having trouble getting it where I want it here. Okay, so V3 is 12 volts, I3 is 2 milliamps. So R3 must be 6 kilo ohms. Okay, now all that we have left is to find our voltage source. So there are a few ways of doing this. I'm just going to pick one way. One way would be to find our total resistance. And all of our resistors are in series, and now I know them all, so that's just going to be the sum of all of these resistances. So 1K plus 2K plus 6K plus 3K. So we have 9, 10, that looks like 12 kilo ohms there. And we do that because that actually gives us our source current if we're looking for it. We're not really looking for our source current because, remember, this current down here is our source current. So if we're looking for E, that's going to be our source current times our total resistance. Again, true of every circuit out there. Your voltage source has got to be the product of the source current throughout the circuit times the resistance of the circuit. That's just Ohm's law. So we've got 2 milliamps of current throughout the circuit and 12 kilo ohms of resistance. So that means we must have about 24 volts at the source. And there's actually another way of figuring this out, and that is, remember when we looked last week at Kirchhoff's voltage law that says the sum of the voltage rises minus the sum of the voltage drops around a closed loop has to equal 0. So let's just write a KVL equation starting here. I'm going to add my 24 because going from in that clockwise direction, that is going from minus to plus, so that's an increase in voltage. And here we're going to see a drop in voltage, so I'm going to subtract my 2, I'm going to subtract my 4, I'm going to subtract my 12, and my 6, and that should equal 0 as I get back to where I started with this. Now let's see if it does. I have 24 minus 2. Let's see if I can move this over just a touch. I've got 24 minus 2, which is 22, minus 4, which is 18, minus 12, which is 6, minus 6, which is 0. So what I found there was, yes, Kirchhoff's voltage law was upheld. And this is really great news because this pretty much tells us that all the work we did is probably right. And this is what's so great about circuit analysis, is that there are so many laws that you can use to check yourself and to make sure that you did things right, that it's really hard to get things wrong. Like, you know that those voltages have to add up, those voltage drops have to add up to the source. And if they don't, there's something wrong. And we found all of those using Ohm's law in the first place, and Ohm's law has to be upheld at every point in your circuit. So we can be pretty sure that we did this right, which is great. Okay, let's try another circuit, and this time this is not so much a series circuit, because what we want to do is work on that Kirchhoff's voltage law idea again. Remember, Kirchhoff's voltage law says that the sum of voltage rises minus the voltage drops around a closed loop have to equal 0. So I'm going to use that to my advantage, and there's like 3 loops we can use here, really, and I'm going to draw them all. So we can use a loop here, I'm going to call that 1. We can use this loop here, I'm going to call that 2. We can even go all the way around the outside of the circuit, and I'll call that loop 3. And let's just write equations for all of them, because I think for the 1 and 2 loops, only one unknown there, so we can find that pretty easily. For the loop 3, we'll save that till the end. All right, so let's work with loop 1. Okay, so loop 1, if I'm going to write my equation, I'm going to start here, and I'm just going to go until I encounter my first voltage rise or drop. Now this is a voltage rise because in the clockwise direction we're going from minus to plus. That means something is increasing. So I'm going to add that. And then when we get to our next voltage to consider, we have a drop across our the resistor, the 1 k ohm resistor. And the drop there, we know that it's a drop. Well, actually we don't know it's a drop. We're assuming it's a drop. We drew in the plus and the minus. It's a guess. It may be wrong. We'll see. But because we're going from plus to minus in that clockwise direction, I'm going to subtract V2. That's an unknown voltage there. And then when we get to our next voltage, we see that that's going from minus to plus, again in that clockwise direction. So that's going to be another plus 8. And then we get back to where we started, so we have to set that equal to 0. When we solve for V2 and we move V2 to the other side, it becomes positive, and V2 has to be 18 volts. Now there's an important thing to note here. That's a positive 18 volts. So what that means is we chose the direction correctly when we put in the plus and the minus for V2. Okay, so I'm going to write in the fact that this is 18 volts. Okay, and just kind of keep that there. Okay, let's look at our loop 2. So for loop 2, we're going to do exactly the same thing. Let me scroll down a little bit. So for loop 2, I'm going to start here, and I'm going to go in this clockwise direction again, and when I get to this 24 volt source, it's going from minus to plus, so that's a rise of 24 volts. And then as I continue around, I get to my 10 volts there, and I don't know if it's a source or if it's a resistor. It just doesn't matter. I know that it's a drop because it goes from plus to minus in that clockwise direction. So that's just going to have to be a minus 10. So it doesn't matter if it's a source or it's a resistor, because we care about the direction of that voltage, not necessarily what it is. So you can't just add all of the sources. Some of them may be going in the opposite direction of the original source. You'd have to subtract it then. So you have to pay attention to the direction. And then I'm going to continue on through this loop here, and I encounter V1 going from plus to minus, so I'm going to subtract that. And then I get back to where I started, so that has to equal 0. So I'm going to solve for V1 by pulling it over to the right, so it becomes positive, and that means V1 must be 14 volts. 24 minus 10. Okay, so I'm going to make a note of that. All right, now let's get rid of this here. And now let's look at our loop 3. Okay, loop 3 is going all the way around. Okay, loop 3 is going all the way around. So I'm going to start here. And when I encounter the 24, that's a rise, so that's plus 24. When I get up here, I'm going to the V2. I don't need to worry about that 10 volts anymore because I'm taking a different path. So I've got plus to minus, and I said that was 18. So I'm just going to go ahead and put in the 18 there and see if this works out. So I'm just using this third loop to check what I've already done. And then when I encounter the 8 over here, that's a rise of 8 because we're going from minus to plus, not because it's a source, but because of the direction. Minus to plus is a voltage rise. And then I'm going to continue down here, and that's a drop of 14 because it's going from plus to minus. And then here I get back to where I started, and that has to equal 0 if Kirchhoff's voltage law is to be upheld. Okay, so let's check this. 24 minus 18 is how many? That's 6. Plus 8 is 14. Minus 14 equals 0. So our third loop actually confirmed what we learned from the first two. So we didn't do any circuit analysis here except to say that we didn't do any circuit analysis here except to use Kirchhoff's voltage law. There were no resistors that we could combine here. This is not a series circuit. I just wanted to practice with our Kirchhoff's voltage law for this problem. All right, let's work with this circuit. We're just going to apply a little bit of what we know to our circuit here. So in this case, we want to figure out, I guess, what our resistor values are. Okay, so this is not an open circuit. This is actually a circuit where there are things going on elsewhere in the circuit. But all of these resistors are in series, meaning my current through R1 is equal to my current through R2 is equal to the current through R3 because they're in series. Let me move that back up just a touch. Okay. Not very good at driving this thing yet, obviously. Okay, so what we want to do is find R1 and R3. So what we want to do is look here at R2. Now we know what R2 is. We know that it's 8 ohms. We also know the voltage on one side and the voltage on the other side. So what does that tell us? That tells us that V2 is going to be the voltage on this side minus the voltage on this side. So +4 minus a -4 means that we have an 8-volt drop across R2. Now what does that do for us? Let me draw this in. So we have a plus to minus 8-volt drop here. What that does is it gives us a place where we can find the current through each of our other resistors, okay? So the current here, we're going to call that I2, is going to be V2 over R2, which is 8 volts divided by 8 ohms, or 1 ampere of current. So that means we have 1 amp of current through each of our resistors. And if you want to draw that in, 1 amp, 1 amp, 1 amp. Okay, so now we should be able to find R1 and R3. So first we need our voltage drops across each. So the voltage drop across R1, which is V1, would be 12 minus 4, or also 8 volts. And the voltage drop across R3, which is V3, would be a -4 minus a -8, which would be 4 volts. So we have 4 volts drop across there. Therefore, R1 would be V1 over I1, again, just Ohm's law. So we've got an 8-volt drop there, and 1 amp through the resistor means we have an 8-ohm resistor. So 8 ohms. And then for R3, we have V3 over I3, or 4 volts over 1 ampere of current, which is 4 ohms. So we must have a 4 ohm resistor there. Okay? All right, so make sure you review Ohm's law and your Kirchhoff's voltage law before we move on to your parallel circuits.